So here we have a hypothesis test, B, for a proportion. So I want to test the claim that the proportion of people who own cats is larger than 80% at a 5% significance level. So the first thing we should do is establish the null and alternative hypotheses. So the alternative hypotheses will never have an equal sign in it. And the null hypothesis will have an equal sign. So in this case, I want my alternative hypothesis to be the claim that the proportion is larger than, greater than 80%, which is 0.8 at a decimal. The alternative hypothesis I chose to be the proportion for the population P is going to be less than or equal to. It could have been P is equal to 0.8. That would be a suitable null hypothesis. Now the sample proportion, that means we had to have some number of people that we surveyed, and then of those people, a certain number ended up being positive for whatever we're looking for, in this case, owning cats. So here I'm giving that based on a sample of 300 people, 85% own cats. So the 85%, that would be my sample proportion, which is sometimes called P prime. Often it will also be called P hat. So sometimes you'll see that this is P with a little hat on top. So P hat, P prime, they're the same thing. They're the sample proportion. In this case, I decided to multiply the sample proportion times the number of people to identify that 255 people said they owned cats out of the 300. And I need that information to use StatKey to run a simulation to try and figure out if the sample is significantly different than 80%. So some results from StatKey. First time I ran the simulation, I entered my data of 255 people out of 300. That gave me a sample statistic of 85%. And I'm comparing that with our default, our null, our assumption that 80% of people have cats. And we're trying to see, is that significantly bigger? So of the 7,000 samples that I simulated here, I found that 16 out of 1,000 of those ended up having 85% or more of those people had cats. So, you know, that's what, 1.6% of the samples. So is it unusual to find 85% or more when you're expecting 80%? Well, if it happens in this case, you know, around 1% of the time, that's kind of unusual. My threshold for what unusual means is 5%. So I'm under the 5% threshold, so I would say, yes, this is unusual. So I do have sufficient evidence. So I'm going to reject the null here. And the reason is my p-value of 1.6% is less than our significance level, which is 5%. And the significance level is how we decide if something's unusual or not. And so something's unusual if it's a small probability. The question is, how do you define small? That's what the significance level is, how we define small in this case. And it's relative to the kind of situation. So I ran the simulation again. I got a slightly different p-value the second time I ran it. I got a p-value of 0.14. So that would be 1.4%. So that's my p-value. Notice we're using p for p-value. Again, the p-value is related to the sampling distribution, where you also have p, which is the population proportion, and p hat, which is the sample proportion. So we got to keep those three straight. They are totally different things. My p-value was less than my significance level. That's what we usually call alpha, which was 5%. Okay. And if that's the case, if you do have a smaller p-value than your significance level, then you get to reject the null hypothesis. And that means you get to accept the alternative. And the alternative, that is the population proportion, the percentage of people who own cats, is actually greater than 80%. Right, so we are accepting that here. We have enough information. So this is what's called a left tail test. Oh, sorry, a right tail test, because I'm on the right side. Another thing to note. Let's take another look at another example. Here, I want to test the claim that the proportion of people who own cats is significantly different. So significantly different means not equal to. So here, I can say that I don't think that the proportion of people who own cats is 2%, 20%. The null would have to be equal to then. So a null is always an equal to, a less than equal to, or greater than or equal to. The alternative can't have an equal. So this is not equal. I did some sampling and I found that 25% of a group of 100 people own cats. So my p-hat, my sample proportion is 25%. N is 100, 100 people. That means 25 of them had cats. I ran that through StatKey again. Here I found, now this is a two-tail test. In a two-tail test, this number and this number combined end up being your p-value. So if I add 12.8% to 12.8%, I get 25.6%. And so that's pretty high probability of that happening. So in this case, I cannot reject the null. So I'm going to fail to reject. Now, I didn't even look at my significance level, and it turns out in many hypothesis tests these days, they state the p-value and they leave it up to the reader of the article to decide whether that's significant or not. But sometimes it's a good idea to go in and state, hey, in this situation, we think a 2% significance level is important. But sometimes that significance level is not even stated in certain studies. They'll just state what their p-value was, and then they'll say, yeah, we think that's significant, and they'll leave it up to you to say, yeah, I agree, or no, I don't. In this case, this is way above, right? So we failed to reject. So we have no evidence that the proportion of people who own cats is different than 20%. So does that mean you have to accept it's 20%? No, go do some more research if you really believe it's not. But this particular sample does not give us enough evidence that it's different. It's close enough. 25% is close enough to 20% in this context. Okay, so let's run a new example in StatKey. So here's a homework problem that you will likely see. So let's see, we want to test the claim that the proportion of people who own cats is smaller than 40%. And we're going to use a 1% significance level. So since we're going for smaller than, let's get a new screen, then we're going to go with an alternative hypothesis that the population proportion is less than 0.4. So the null hypothesis could either be that p is equal to 0.04 or p is greater than or equal to, 0.4, 40%. So you go with either of those. It kind of just depends on the context. In this particular homework problem, I don't think I have that choice. So let's see, we don't want mu, we want p. P is less than 4%. That's definitely my alternative hypothesis. So my null hypothesis in this case is going to be greater than or equal to. Since I'm going with left than for alternative, this is a left tail test. And then my sample data is that 32% of 100 people. So sometimes you have to do a little multiplication to figure out x, which you need for StatKey. So next we whip out StatKey. So I should copy that. Sample data, paste it into my notes. Hopefully you write a lot of stuff down when you're taking notes on these problems. It's a good idea. All right, so StatKey, there you are. And we are doing a randomization hypothesis test for a single proportion. We need to edit the existing data and state that 32 out of 100 are the sample data. And then our null hypothesis is 40%, so we need that too. So we enter in our sample data by editing data. We enter our null hypothesis right here. And then in this case, we are running a left tail test. We'll check that in a minute. And we just need to generate a whole bunch of samples, do at least 6,000. You can always do more. And then left tail. Now it's going to default to 25% in the tail, and we are going to adjust that by plugging in our sample data, which was 32%. All right, so we get, if we believe there's 40%, we get a sampling distribution based on that and the sample data. We plug in our sample data and we find that 6.7% of the 8,000 samples that we simulated ended up being less than or equal to 32%. So that's my p-value. All right, so I ran stat key, and stat key gave me a p-value of 6.7%. And in this particular problem, what was our threshold? Our threshold was a 1% significance level. So we are way over 1%. Okay, so note, alpha was 1%. And in this case, my p-value is greater. So my p-value is greater than alpha, which means, hey, that's not unusual at all. If it's less than alpha, then it's unusual. So 0.067 is greater than 0.01. So this means we fail to reject. Because this data is not unusual. This data is not unusual. It's close enough to what was expected. Unusual, close enough. All right, so that's the key of hypothesis tests. You have some assumption about the population, you collect some data. You then either run a simulation or run some crazy formulas, which we'll deal with in a couple of weeks, and you calculate what's called the p-value. P-value is the probability of finding such a sample given the assumption, right? So it's probability based on given information. And we found that, hey, given that it's supposed to be 40%, 32% isn't that much lower, no big deal. We can't say it's not 40%. We have no evidence here, right? So we have insufficient evidence. So I can just check that out by plugging it back into the system. Let's see, bigger. So we believe our p-value was 0.067, 6.7%, which is not unusual, which means we fail to project, reject, and submit, and I got them all right. Once in a while, the p-value from the simulation will be a little bit different than what was expected by the computer program here. So if you think you ran a good test, then just send me some information from your notes with the message your instructor option here, and I'll check it out and see if I believe you were close enough or not. Sometimes it's hard to program that into a computer-graded system like this, but we do our best. So that's a few examples of hypothesis testing with proportions. Hopefully this is starting to make a little more sense. We're going to have another few weeks playing with it, so you get time to get used to it. For now, hopefully you're getting used to the notation and some of the steps. If you have any problems, send me a note. I'll be glad to help. Take care and do good math.